Hi, good morning all. I'm Rama from Microsoft. I work as a RAS team lead. We have Drew from Microsoft and Ivan from Micron and Carlos from AMD. Uh, in this talk, we'll go over hardware fault management work streams. We have some sub projects within hardware fault management. And we'll give you overview of this work streams update. We may not have much time to go deep dive because we only have 30 minutes. We started this work, OCP hardware fault management, around 5 years back. Started with 3 companies, Intel, Meta, and Microsoft. Now we're happy to say that we have more than 15 plus companies, the participants across silicon vendors, firmware vendors, hyperscalers, enterprise customers. You see the list silicon, you have CPU, GPU, and memory vendors, a lot of diversity. And Drew will cover some of the things.
All right, so yeah, I'll talk about the vision. I'm Drew Walton. I'm really excited to be here because we're kind of in a new era where a lot of competitors are getting together and saying, hold up, we have this really complicated problem. It's fault management, and error handling is one of the most complicated things to do. We've had 9-month-long debugging marathons where at the end we weren't sure that we'd really solved the problem, but it seems to have gone away. These are challenging problems, and what we've realized is that a lot of the plumbing that we're building isn't proprietary. And if we can create an ecosystem where we meet fault management needs of hyperscalers, we can enable silicon vendors to compete with each other while still doing something that meets a standard where we can plug their things into it pretty easily. And so that's what the first bullet is all about. And so we're creating a common fault management interface for SoCs and devices where our dream is that you plug a new thing into a data center, and if you've met our standards, you just start talking to us, and we start seeing your errors. And then if it's a particular vendor's product, they'll have a tool for analyzing that, and we'll run that somewhere in our data center. That tool will spit out some answers, and we will plumb those answers back into the machine over the same standard interface so that people can try fault management features out without a huge investment. They can get the right telemetry without reading 10,000 pages of registers and making wild guesses. So we're building these all based on first principle understandings with the vendor's help. And that's the big deal, is that the vendors are going to compete, the Intel, AMD, Micron, SK Hynix, NVIDIA, you name it. They will compete with how well they log errors and applying knowledge of their design in the analysis tools to tell us what's going on. And by doing that, we can drive broader RAS participation from new corners of the industry. Imagine we have standard common error records, and those error records are gathered universally by everyone. And it may be different for every vendor's product, but then Microsoft can learn from what Google learns, or Meta finds a problem, and maybe Pure Data. There can be another company that's feeding these error logs in, and we all benefit from suppliers understanding that. And that infrastructure is shown in the drawing here. We have in-band fault management agents that we've been working on. The RAS API is a lot of what I'm talking about, where we have plugins, allowing us to configure, to get error logs, drive actions, and inject errors from out-of-band and in-band. In the fleet memory fault management work stream, we're designing tools for analyzing memory errors that are on the let's see, it's the right side of this drawing. And on the left, we're making sure that we get the right error logs. And then in the GPU RAS meeting, we've been figuring out, okay, what are the RAS standards for GPUs, and accelerators, and how do those plug into this ecosystem? The end result will be that we're solving end user problems, and what we're doing is we're giving the suppliers incentive to develop tools that meet our needs, but they're useful in a way that they meet your needs too. And by doing this, where the vendors are willing to put effort into the tools because of it addresses so much of their end users' needs. With that, I'll hand it back over to Rama to talk about our work streams in particular.
Yeah, like there are few work streams here, right? The first one is like hardware fault management main work stream that focuses on the framework principles. Hey, what kind of workload environments you have, what is the RAS requirements, right? We have already released 1.0 version of that, okay? And that is mostly focused on out-of-band fault management, okay? And as the next version, we are focusing on adding some in-band fault management requirements. And in addition to that, in 2.0, we are expanding all the common RAS features into that document, okay? This first work stream provides guidance to all other sub-work streams, and it also has overall requirements, okay? Then next we have two component and system level with focus on GPUs and memory, right? I think we just made on the GPU 1.0 contribution. We had a separate talk. We won't be going details. A few people who missed the talk will just give high-level overview. The goal of GPU RAS requirement document was how to focus on the training and inference workloads. They have different requirements compared to general purpose compute because your workload almost spans across data center super AI computer, okay? One critical performance issue, slowness because of link health or error storms can impact full data center scale workload wise impact, okay? And we just contributed that 1.0 version. This is right now is a CLA based work streams across AMD, Meta, Microsoft, Google, and NVIDIA, okay? And any feedback, once we release it, if you have some feedback, you can provide through hardware fault management work stream, okay? And then we have a memory focused work stream, which focus on the memory error logging standards and also main focus on analysis tools. Sometimes if you find memory error, it can be coming due to DIM issue, it can be platform level issue due to voltage and other temperature issues, or it can be from memory controller side, right? This work stream will focus on how do we standardize analysis tools, how do we differentiate different repair actions required, right? The goal of this work stream 1.0 before next global summit, we'll have the 1.0 version of that, and Ivan will go full details into what is in that spec. And next one focus on RAS API. This is focus on interfaces, mostly if we see at hyperscale infrastructure, you have big diversity, right? You have compute devices, CPU vendors, multiple vendors, memory vendors, you have I/O card vendors, right? How do we seamlessly interact with hyperscaler requirements? Hyperscalers, generally to maintain fleet health, there is a cloud RAS focused services, like telemetry service and predictive health maintenance. Because we have big data, we want to use this data to predict next failure, what repair action can be taken, right? And we have debug service, which can help root cause issues with meeting some different SLA times, right? We have a diagnostic service to identify exactly the flaw. For all these services to work seamlessly, right, we want to standardize that interfaces so that we don't want to interact with each vendor different custom APIs. That is the focus, okay? That will help RAS feature discoverability, how do we configure RAS, okay? What actions you can take. That spec also we are targeting around before global summit. This is also other CLA based work stream, And this is open CLA based, like anybody can sign that CLA and can participate. Okay? And for the main hardware fault management work stream, we meet every week Friday 2 p.m. I know it's not a good slot, but people spend a lot of their personal hours to focus on this. That's where Friday we get some additional bandwidth. Okay, and there is current OCP fault management infrastructure requirement version 1.0. You will see next week GPU OCP RAS focus release spec. And we are welcoming like other participants. Okay, we have some wiki page which has more details. And please reach out to any of us, like Rama, like I'm from Microsoft, Yogesh from Intel. We lead this project, and there are a lot of contributors. Like there are like almost like 30 plus people joined sometimes in this call. A lot of collaboration. Thank you for all the support. I'll give it to Ivan to go over memory.
All right, thanks, Rama. I'm Evan Pearson. I'm from Micron. I get to represent the FMFM work stream today, which is the second FM there is the fault management part. The first FM is fleet scale memory. So this is the DRAM-centric portion of it. Rama said I'd get into full details, which might be an exaggeration. I have 3 slides. Basically one that has the vision and how this started, one with current status, and one with future plans. So how the FMFM began, it got spun out of the overall HWFM work stream as we realized that kind of the memory subsystem needed a little bit more focus. So the goals are to get the DRAM experts and the silicon vendor experts together and provide fault management actions and RAS actions and standardize kind of the I/O and error logging portions for the memory subsystem at fleet scale. So a couple main goals there to be able to reduce friction and solve end user memory handling issues and avoid those 9-month debugging sessions like Drew was mentioning, at least one related to DRAM. And drive innovations in DRAM reliability. There's a lot of data at this scale in the data center. So being able to capture a lot of that data and get it fed back can help drive innovations in ways that we haven't seen previously. So standardizing the memory error logging formats and interfaces, both on the inputs and the outputs, and a vendor agnostic abstraction for the error handling and analysis. And the reasoning for that, it causes a lot of pain both on the error collection right now and on the error analysis for silicon vendors, fleet operators, DRAM memory vendors. Everything is currently fairly non-standard, and it requires kind of a unique bespoke solution each time we're working through one of those large issues. So that's kind of the background. Current progress, the flow chart here on the right is actually basically identical to the one presented last year at the summit, which is good. We've been developing kind of around this model. So that's remained, the overall vision there has remained pretty static, and that green box in the middle is the vendor-specific fault analyzer. So a lot of the work has been around standardizing the I/O into and out of that block. Currently focusing on DDR, DIMM logging capabilities, focused on DDR5 since that's the current generation in 3 categories of boot time, runtime, and airtime, crash time. So where we are right now, the I/O of that has been broadly defined, and we're working on kind of the specifics of the standardization and the data formatting around that. And then the DFA RAS actions there out of the DRAM fault analyzer and the CPU vendor fault analyzer. Just some examples of that could be things like page offlining, in-field repair, things that can be automated and allow a system to stay up and stable even if there is an error in the memory subsystem. And then DIMM replacement, no action, et cetera, just to give a good, well-informed action there. And you'll notice the memory error yes, no split there in the middle of that block. If the CPU vendor identifies that it's not a memory error, it skips over the DRAM fault analyzer and straight back to the CPU analyzer. However, if it is identified as a memory error and then the DRAM fault analyzer maybe doesn't know what to do with that, it can still feed into the platform or CPU analyzer, and maybe there's an additional action that can be taken there. So all of this can feed into the overall RAS policies. And then where we're going, so version 1.0 is not quite finalized. We're kind of working through the details on the data structures and things like that. But the DDR5 has a good outline right now, so we're estimated completion of second quarter of next calendar year when we'll have a version 1.0 spec available based around DDR5. And we get a lot of questions on when is HBM coming, when is LP coming. That's kind of the rough scope right now for version 2.0 or a version next. LP is becoming a much larger deal in the data center, and of course HBM is already there in a lot of cases. So a lot of the standardization will be important there as well. And then I'll close with a call to action. Anybody that's interested in memory errors in the memory subsystem in servers at fleet scale, please come join us. We could use your feedback, your inputs. It's been a great collaboration so far. We meet every other Tuesday at 7 a.m. Pacific, so kind of on the opposite end of the other one, like a little early for those on the West Coast, but it's a global team that joins, so people are joining from all over the world. And then links there to the calendar and how to get involved. But please reach out to any of us or anyone involved in fault management if this is something that interests you. It's been a great work stream so far. And with that, I'll pass it to Carlos, and you can cover the RAS API.
Thank you, Evan. So good morning. My name is Vallin. I'm a systems architect in AMD working on RAS. So while Rama and Drew cover the big picture and Evan also cover a little bit of the memory challenges, now we're going to talk about how to put it all together in a vendor agnostic manner, right? So that's the purpose of the RAS API workstream. And so the vision of the workstream is to define a standardized communication mechanism between devices and the RAS management software in the data center. And so the envision benefits of this is that now hyperscalers will be able to reduce the amount of complexity maintenance in their development of this RAS management software, right? By allowing them to have this standardized way that, basically a plug-and-play interface so that next time they get this next-generation GPU or next-generation CPU, it all works. They don't have to go and develop that again, right? And then the second benefit is that it's make it easier to do the day-to-day fault management in a large fleet of devices that are likely going to be of a diverse set of suppliers, right? And so just to recap, right, standardized way to dynamically discover RAS capabilities of devices, be able to configure those capabilities, and then be able to use them with minimal investment, right? So in the last year's Global Summit, we presented an update where we were looking at or evaluating the idea of implementing this standardization layer at the hardware level, and that we were looking at to build on top of that and look at other alternatives that could span across firmware and software. And so as more vendors started joining the discussion, we quickly realized that we really had to do some extra work to really find that sweet spot on the stack of where to implement this abstraction, right? While still, and but this was necessary work, right? It was necessary to get us all aligned to move forward, but obviously impacted a little bit of the initial estimates that we had on releasing the version 1.0 of the spec. But nevertheless, now we have agreement amongst all of the participants of the work group to place that abstraction layer point higher in the stack, right? And so instead of expecting it to be implemented at the hardware layer, now we move it up and at the same time, we continue to maintain the original objectives of the RAS API workgroup, which is standardized set of commands or opcodes for dynamic discovery of these RAS capabilities. Implementing separate error queues per severity and per error reporting path, inbound or out-of-band. And also standardize the input and output payloads that are going to be used with these commands for configuring or requesting RAS actions and configuring the error queues for error reporting. We believe that, and actually, if you look at the diagram here on the right, it illustrates this concept in a high level. The abstraction layer now is in between the the management software, whether it's inbound or out of band in the data center, and the particular implementation the device vendor picks for talking to its hardware, right? And so this is a concept that we have introduced that we're referring to here in this picture as plugins. These are going to be connections to the abstraction that the RAS API provides that may be enabled in the industry by the particular vendors that want to go one way or the other. So, we have talked about a CXL CCI plugin that may have some enablement to be done in the MTBF and the CXL consortium. Also talks about a PLDM plugin that will have their enablement be done outside of OCP and the MTF and PMCI, and then an ACPI plugin for the inbound path as well, right? So we believe that this direction is going to promote vendor diversity and fair competition. You no longer have a vendor that is found itself in a competitive disadvantage position because another vendor has been implemented this particular implementation for a number of generations. And so as long as the implementation in the hardware and the full stack actually can abstract it to the RAS management software in the data center to that picture, right? 4 error queues, a point for discovering and requesting RAS actions, then we're giving the ecosystem freedom to go and make that work, right? We'll still envision that the plugin level will set some ground rules and boundaries at the spec level, right? So that it can continue to be plug and play with the OCP RAS API. At the same time, we believe that this will also enable faster vendor adoption, right? By just allowing this coexistence of diverse hardware, software protocols, and communication protocols, and the ability for the vendors to still compete with each other, right? So that pretty much summarizes what we have been up to in this work group. In terms of call to action, get involved. Would love to hear your thoughts, especially if you have experience defining a scalable software API, which is now the scope that we're looking at. I would love to have you involved and give you your thoughts on that. We meet every other Wednesday, 8 a.m. Pacific. Here at the slide, you'll have a number of links and resources to join, particularly the one to sign the CLA. Reminder, this is a CLA workstream, so you have to sign that CLA in order to participate. So with that, I think we have a couple of minutes for questions.
We have 5 minutes for a question. Any questions?
No brave souls?
Can you get to the mic?
There's a mic up here.
I'm just wondering, any of the APIs that you work on adopts or correlates with the MTF framework for discoverability, feature discoveries, action taking?
Yeah, I'm assuming you're talking in the context of RAS API, right?
Yeah.
Yeah. The idea is that if we go back to this picture here, if I can go back to it, is that all of that enablement in the ecosystem could be leveraged by the vendor, the hardware vendor, on those plugins, right? And so there will be inherited requirements driven by the higher API at the software layer, right? That will have some set of expectations that the lower layers need to go and provide as source, right? Or have a pathway to go and drive it the other way around. And so that's the reason why we're going with this direction, is that then the vendor can go and leverage that ecosystem like the MTF, PMCI, CXL consortium, to then go pick a solution that could be better, faster, drives more value, or target specific use cases.
I have a question. Can you say a little bit more about what is PLDM plugin? What kind of PLDM types will be supported by it, and what's your expectation?
Yeah, of course. So in this particular picture, the PLDM plugin, or the context we have been discussing in the REST API workgroup, is to use specifically PLDM type 2, so platform and monitoring and control. There are a number of other things you may have seen in other of these presentations that are related to new ways of doing things in PLDM, like for example, the file I/O and transfer that we're also considering. So it's not limited to just type 2. That's just like the first idea that we picked, or the starting point. We're just seeing the enablement in the industry to see what makes sense to adopt.
Okay, thank you. Any other questions? We still have a few minutes.
Hey, Carlos. Are you planning to have commands also for control, just telemetry, or you're also planning like boot control or stuff like that for inbound support?
We're really starting with just the core requirements and pain points we want to solve on the RAS environment, which really is simplifying the error reporting, like across different vendors. No matter what the vendor is, you shouldn't need to do and implement different ways of doing it if it's an Intel or an AMD or an NVIDIA or et cetera, right? And so that's number one. And then number two is having the ability to have the configurability per severity, right? And in terms of the actions, it's mostly going to be related on any serviceability or mitigation actions that you could do as a result of that telemetry you're getting from the error sources. For example, you get a memory error with the data that Evan covered here in the FMFM, and with that information, you're going to have some piece of analyzer that could be vendor specific, right? That then tells you, this particular memory error qualifies for a PPR action, a runtime post-package repair, for example, right? And now you have the same pipe going the other way around with standardized set of APIs and commands that says, okay, this particular SOC supports post-package repair. And then you'll be able to then inject with those standardized payloads for an action defined as a post-package repair with a standardized subcode to then go and say, SOC, I don't care who your vendor is, just go apply post-package repair for this. So at this point, we're just focusing on that core problem. We haven't really expanded into some of the other things around bulk telemetry and other telemetry sources. So at this point, we're really focusing on RAS telemetry. And after we get our hands on what we want to do there, we can look to have synergy with other sources, type of telemetry sources.
Time for one quick question.
Double-clicking on what you just said with respect to the RAS API and the actions we perform, there is definitely a way to kind of do AI on it, like where you can start predicting those failures. Are we thinking in those lines?
Yeah, I mean, that's something that we've always had in mind. And it's funny, we still want to crawl before we walk, like we have more fundamental problems that we need to solve. But yeah, that's something we're looking at.
Yeah, I'd like to add something to that, and Jackson and I know each other really well. But one of the thoughts is that the fleet memory fault management folks are going to use AI in their tools in some cases. The other thing that happens is, let's say that the RAS API sends an error log up and that we analyze it and we decide that we want to take action on that log. Well, the supplier may say one thing, but we as a hyperscaler may have a gigantic fleet and when we use that action, maybe it doesn't really fix the problem. It doesn't do quite what we want. So what we may do is we may look at decoded error logs. We may look at the action that was suggested, apply another layer of AI on top of that, treating it like an expert system input to another model. And so there's nothing inherent in what we're doing that won't allow an end user to take the data that we're generating and build upon it and do something even smarter for their fleet and based on their experience.
Yeah, and you can always enrich that data with other sources that will make your models have more parameters and make it smarter and smarter and just iterate over it.
actually hyperscalers already published some of the error prediction work. For example, storage devices has industry standardization for many years, right? Then the next one is memory. One of the challenges we have is for computing devices, prediction like CPU, GPU, where like timeouts in like milliseconds, nanoseconds, right? That is the one of the critical area like we want to focus on, right? There is already published papers from different hyperscalers on error prediction because we have the big set of data, right? And a lot of them invest in AI, and we already do that work. Some are proprietary, some we want to enhance for standardized telemetry for AI. Yeah.
All right, at this point we are out of time, but let's thank our presenters.